20,000 lives were extinguished in a matter of minutes when the ocean delivered its most brutal warning to Japan in 2011. The sea knows no mercy, sending a wall of black water to swallow entire cities in a single surge. Why would a nation invest $12 billion to construct a concrete scar stretching across 400 kilometers of its coastline? It seems like an insurmountable task to challenge the horizon, but this massive shield represents the largest defensive fortification in human history, built to answer a question that continues to deprive engineers of sleep. A single calculated question remains at the center of this architectural defiance. Can a wall, regardless of its immense scale, truly halt the absolute fury of the sea when the tectonic plates inevitably shift again? The equipment gradually reshapes the shore, but the true threat lies where sunlight never reaches. Japan sits directly atop a geological time bomb rather than merely floating upon the waves. The camera glides along the seabed to reveal the collision point of 4 titanic tectonic plates. One can notice how these stone continents constantly grind, push, and struggle for space in a zone known as the Ring of Fire. This subterranean friction generates more than 500 earthquakes every single year. The Earth here never rests, and the tension accumulates in the dark silence of the crust. Transition to the next level of destruction occurs when this underground pressure finally snaps. The seafloor is catapulted upward with unimaginable violence, displacing the entire water column above it. This movement does not create a standard wave, but rather a moving mountain of water with immense kinetic energy. In 2011, the existing defenses of 7 or 8 meters were treated as mere toys. The water surged over them as if they were invisible, and the concrete was pulverized under the weight. It is visible how the old steel was twisted into useless scrap by the sheer force of the inundation. At first glance, the old walls appeared sturdy, but in reality, they were completely insufficient for a disaster of this magnitude. Engineers realized a terrifying truth during the aftermath. Simply building higher was not enough. They had to reinvent the very concept of a coastline to survive the next inevitable event. The objective shifted from total obstruction to the vital necessity of buying seconds for the population. The process is only gaining momentum as the focus turns to survival windows. This extra time allows residents to reach higher ground before the impact occurs. Construction of this 21st century Great Wall began with the understanding that every meter of height equates to lives saved. Huge blocks of reinforced concrete are placed with millimeter precision to form a continuous barrier against the deep. Thus, the transformation of the coast moves into its most ambitious phase of engineering. 400 kilometers. This is the total distance across which a continuous line of military-grade reinforced concrete must stand to repel the force of an entire ocean. Why does the engineering for such a massive structure begin in a laboratory rather than on the shoreline? One might assume that construction starts with the pouring of foundations, but in reality, every centimeter of the barrier is the result of simulated catastrophes in giant water tanks. Scientists repeatedly recreated the apocalypse by hurling tons of water against scale models of walls to identify precise points of structural failure. The height of a barrier only looks like the primary defense, but tests revealed that if a wall were merely tall, the immense pressure of a wave would snap it at the base like a dry branch. One can notice how the water in the test tanks crashes against the miniature models with calculated ferocity. The key to survival was not just the exterior shape, but primarily what remained hidden beneath the surface of the Earth. At first glance, the coast of Japan in the Tohoku region appears stable, but it is composed of soft, unstable, and treacherous sand. Constructing a concrete rampart 15 meters high on such a surface is equivalent to balancing a heavy truck on top of a saturated sponge. If a tsunami were to strike this foundation, the ground would liquefy and the entire wall would collapse forward into the sea. But this is just the beginning. The solution implemented by engineers was both brutal and invisible to the eye. Giant drilling machines, resembling equipment from a science fiction narrative, began the process of transforming the geological structure of the coast. These machines did not merely excavate soil. They drove steel in concrete piles to a depth of 25 meters. This is the equivalent of an 8-story building buried completely underground to serve as a structural anchor. They injected liquid cement directly into the sand at high pressure, turning soft beaches into solid, artificial rock. The process is only gaining momentum. The objective was to create an unbreakable root system for the concrete barrier. Engineers ensured that even if a massive wave managed to flow over the top of the wall, the main structure would not tip or move. It would remain standing like a stone sentinel, refusing to cede ground to the hydraulic pressure. With the foundation finally prepared for the confrontation, a massive construction force arrived at the shoreline. Calling this group an army is not an exaggeration, as 30,000 people, including engineers, laborers, and crane operators, occupied the coast. A fleet of heavy machinery consumed diesel and operated 24 hours a day for 7 consecutive years. It seems simple to build a wall, but in reality, the logistical challenge of maintaining a continuous, flawless structure over 400 kilometers was unprecedented. This distance is equal to the stretch between London and Paris, but built entirely of heavy, reinforced concrete. The camera glides along the construction sites where the scale of the work appears hypnotic and terrifying. First came the installation of the steel skeleton, involving thousands of tons of rebar. Metal bars as thick as a human arm were braided into complex cages to serve as the internal frame of the structure. Everything only gets more complicated as the work progresses. Without this dense internal steel lattice, the concrete would shatter under the immense tension of moving water. Then came the introduction of the liquid concrete, often referred to as the blood of the wall. Industrial pumps operated with a constant mechanical rhythm, pushing a gray avalanche of material into the heavy molds. Section by section, the massive blocks began to take their final shape along the horizon. The liquid stream of concrete gradually fills the forms, transitioning into a calm state as the material cures and hardens into a permanent defense. Thousands of tons of reinforced concrete and steel form a barrier that expands block by block, yet a purely vertical surface remains insufficient against the ocean. Why is a flat wall unable to withstand the pressure of a tsunami on its own? It is because the water strikes the structure with the concentrated kinetic energy of a high-speed bullet train. To dissipate this massive force, engineers deploy a geometric strategic asset known as tetrapodes. One can notice these four-legged structures clustered at the base of the fortifications like oversized concrete toys. But in reality, each individual unit weighs several tons, providing a foundation of immense stability. Thousands of these structures are positioned systematically on the seaward side of the vertical wall to create a zone of controlled chaos. When a wave impacts this irregular field, the water cannot strike the primary wall as a single solid hammer blow. Instead, the liquid volume breaks apart, swirling and foaming as it navigates the gaps between the concrete legs. This process forces the water to lose its destructive energy through turbulence. The equipment effectively transforms what would be a lethal strike into a manageable hydraulic push. It is the application of physics to domesticate the raw power of the natural world. The process is only gaining momentum, but a significant logistical challenge arises. Japan remains fundamentally dependent on maritime routes for its survival. Cargo ships, massive fishing vessels, and tourism boats require constant, unobstructed access to the open sea. Constructing an unbroken wall along the entire coastline would result in total economic stagnation. Cities would face financial collapse if their ports were permanently sealed off. Therefore, engineers had to solve the contradiction of allowing ships to pass while stopping a tectonic surge. The technical solution arrived in the form of massive steel guillotinas. In high-traffic ports, these structures are installed with a design that reflects advanced industrial efficiency. There are two primary configurations for these barriers, both engineered for absolute reliability under pressure. The first configuration is the vertical drop gate. A massive steel plate, weighing several hundred tons, remains suspended between two reinforced concrete towers. One can notice how ships pass safely beneath the raised barrier during normal operations. But the moment sensors trigger an emergency response, the massive weight begins its descent to seal the harbor. Seismic sensors detect a magnitude shift deep on the ocean floor, triggering an immediate electronic response. Why must the reaction be instantaneous when the threat is miles away? A delay of even a few seconds could mean the difference between a functional defense and a catastrophic breach. Within moments of the detection, heavy hydraulic motors release their safety locks with a mechanical snap. The steel plate descends with a rhythmic sound of two heavy impacts, sealing the port completely. A vertical wall of reinforced steel now blocks the entrance, creating an impenetrable barrier against the incoming surge. The second type of defense system is even more technically impressive. These gates rise directly from the seabed. They remain lying flat on the marine bed in a horizontal position, invisible and allowing massive vessels to navigate directly over them without obstruction. When the alarm sounds, high-pressure air or hydraulic fluid forces the gates upward. This action raises an instant barrier from the dark depths to the surface level. One can notice how the water churns as the massive structure displaces thousands of liters during its ascent. But this is just the beginning. The primary engineering challenge here is the relentless nature of corrosion. Salt water acts as a corrosive agent that degrades metal surfaces continuously over time. These gates must be capable of functioning with absolute perfection even after sitting immobile for 30 years in a mixture of salt and abrasive sand. It only looks obvious that a gate will move when commanded, but in reality, a single failure or a rusted hinge would result in a city being flooded. The maintenance of these mechanical giants is categorized as a matter of national security. Japan does not limit its engineering to surface-level structures. It gets more complex further on. Sometimes the most effective way to manage water is not to block it, but to move entirely beneath its path. The construction of underwater tunnels represents perhaps the most audacious technical feat in modern engineering. These projects do not utilize standard drilling machines that cut through solid rock layers. To cross deep bays, Japanese engineers apply a method that defies standard logic. They construct the entire tunnel on dry land and then submerge it into the water. This process is known specifically as the immersed tube method. First, workers construct gigantic tunnel segments within the controlled environment of dry docks. 100 segments or more might be required for a single project. Tens of tons of water fill the internal ballast tanks to initiate the controlled descent of the massive tunnel sections. Why is the immersion process conducted with such extreme caution? The descent must be perfectly vertical to avoid structural damage. Sonares and high-precision lasers guide the movement through the murky depths with surgical accuracy. As the two segments finally make physical contact on the seabed, a giant rubber gasket creates an immediate seal between the faces. But this is just the beginning. The immense pressure of the surrounding ocean acts as a hydraulic press, pushing the segments together and tightening the seal even further. It seems simple to rely on gravity, but in reality, the engineers are utilizing the very weight of the sea to keep the interior of the structure dry. One can notice how the equipment gradually covers the entire assembly with layers of protective rock and sand. This process buries the tunnel permanently beneath the seabed, shielded from currents and anchors. Motorists will eventually travel through these passages at 100 kilometers per hour. They will likely remain unaware that thousands of tons of ocean water are pressing down just a few meters above their heads. Once the concrete reaches its full structural strength and the heavy machinery departs, the massive structure begins to function like a living organism. These walls and tunnels are far from being inert slabs of stone. They possess a complex electronic nervous system. Hundreds of specialized sensors are embedded deep within the reinforced concrete walls to detect the slightest physical changes. These devices monitor water pressure, the constant vibration caused by heavy trucks, air temperature, and even ground displacements measured in fractions of a millimeter. Data flows in real time to control rooms that resemble command centers used by space agencies. If a microscopic crack appears anywhere in the structure, the engineers receive an immediate notification. The process of monitoring is only gaining momentum as the structure ages. Should the ground shift by even 1 millimeter, automated alarms are triggered across the network. Because when the stakes involve thousands of lives, there is no margin for error or mechanical surprises. Maintenance becomes a perpetual battle against the corrosive power of the natural elements. Autonomous underwater robots are deployed to inspect the foundations and structural integrity of the submerged base. Simultaneously, specialized teams clear the drainage systems to ensure every component functions perfectly during a crisis. It gets more complex further on. $12 billion and a full decade of labor were invested into this project. The raw truth is that this massive wall will not stop 100% of the water from a mega tsunami of the magnitude seen in 2011. Water may still crest over the top of the barriers, However, technical simulations reveal a crucial factor in the design. The wall is engineered to break the kinetic force of the oncoming wave. It will reduce the initial impact by 30 to 50%. Instead of a supersonic wall of water destroying everything in its path instantly, the resulting flood will be significantly slower. And this is the key to the entire engineering philosophy. The goal is not merely to keep the land dry, but to buy the population precious minutes of time. 5 minutes or 10 minutes can be the difference between life and death. This is the window of time an elderly person needs to reach higher ground. It is the duration required for a school to evacuate hundreds of children to safety. Ultimately, this gray concrete scar, stretching for 400 kilometers along the Pacific coast, is not a symbol of human arrogance. Japan understands that it cannot truly defeat the fundamental forces of nature. Tectonic plates will inevitably move and the sea levels will continue to rise. But this Great Wall stands as a physical declaration of human persistence. It is a message engraved in stone and steel, stating that although the nation was struck down, it has risen again to build a shield. The structure is not a guarantee of immortality. It is a calculated bet on human survival. When the sirens sound for the next disaster, this cold concrete will be the final barrier between the fury of the ocean and the people who live on the coast. One can notice how engineering transforms the instinct for survival into a physical reality. To obtain just 260 grams of gold, a completely different scale of industrial effort is required. Thus, the steel and concrete reach their final purpose in the chain of protection. 19,000 tons of earth and rock must be processed to obtain the precise amount of gold found in a single common smartphone. Why is a precious metal extracted from such an insignificant concentration of ore, and what constitutes its true price? This narrative follows a brilliance born in darkness, charting a journey from ancient rock to the pure gold bars locked within impenetrable vaults. It is a transition that begins in the deep crust of the earth and concludes in the dazzling world of wealth and status. One can notice how gold appears everywhere in the landscape of luxury, from flashy supercars to steaks covered with edible gold flakes that cost several $1,000s per serving. But this is just the beginning. There exists a shimmering golden card once associated with the name of Donald Trump. Rumors circulated that its value reached $5 million, and some claimed that merely holding it could guarantee American citizenship. Whether it serves as a literal symbol or something more tangible, one fact remains clear. Gold has never been just a chemical element. It is power that can be held in the hand and ambition that can be worn. Over 4,000 tons of gold are extracted every single year across the globe. It gets more complex further on. Behind this metallic glow lies a long and intense industrial journey. During the Neolithic era, more than 6,000 years ago, gold was already being utilized to craft jewelry, sacred objects, and specialized household utensils for rulers and the elite. What differentiates gold is not merely its visual luster, but its physical capacity to endure through time. It does not rust, it does not fade, and it does not wear down under environmental stress. At first glance, its value seems tied to aesthetics, but in reality, its permanence is its greatest asset. In a world of constant change, gold is one of the few materials that never needs to prove its worth again. This is why it became an enduring symbol of power, wealth, and systemic confidence. The metal does not wait on the surface. It reveals itself only to those patient enough to search beneath the soil. The process is only gaining momentum. In 1848, a small discovery in California changed the entire course of American history. A handful of bright gold flakes found in a stream triggered the most famous gold rush of the 19th century. Tens of thousands of people rushed toward the west, abandoning entire cities and farms with the single hope of striking it rich. But before the gold becomes a symbol of status, it must be located, and this search leads to two completely different worlds. One can notice the contrast as the focus shifts toward Uganda. This is a land often described as sitting directly atop gold deposits, yet here, the metal does not shine in glass display cases. It hides beneath pools of water and thick layers of sediment. The material remains concealed in the earth, awaiting the first stage of its transformation. $1 a day is the razor-thin margin between survival and starvation for families laboring in the heat. Why do children who cannot yet spell their own names follow their parents into the dry, unforgiving soil with rusted shovels? This brutal environment offers no alternative, as mining here is not a career choice, but a desperate lifeline for those with no other means of sustenance. Families endure a scorching sun that beats down on red dust, sweat, and the remnants of interrupted childhoods. For these young workers, the riverbanks serve as their only classrooms, and heavy metal tools replace toys in their small hands. Gold represents no symbol of status or luxury to them, but rather the singular possibility of surviving 24 hours more. The process of searching for the precious metal is a slow, methodical test of endurance. A day of hunting for gold begins with the activation of a single handheld metal detector and the reliance on a sharp pair of ears. Miners move with a slow, rhythmic pace, keeping their vision locked onto the ground while interpreting every electronic sound from the device. One can notice how a sharp beep provides a momentary flash of hope, though the veterans of the pits do not rely on chance alone. Experienced laborers identify specific geological markers, targeting areas near quartz and slate, where gold deposits historically settle. Once a signal is confirmed, the team initiates the digging phase, and the physical exertion intensifies immediately. The process is only gaining momentum. Pits are carved deeper into the earth, sometimes reaching depths of 10 to 15 meters, through the sole application of pickaxes, shovels, and human muscle. No industrial machinery is present to assist in the heavy lifting or structural reinforcement of the shafts. In certain locations, miners use rough tree trunks to prop up the ceilings, yet the threat of a sudden collapse remains a constant reality. It only looks obvious to outsiders that the work is simple digging, but in reality, the laborers must crawl through narrow tunnels, barely wide enough for a person to lie on their side. Every excavated hole functions as a high-stakes gamble that could result in total failure, or the discovery of rock worth an entire month of wages. Heavy sacks of earth are secured with ropes and hoisted to the surface using rudimentary pulley systems, where they are stacked in massive piles to await crushing. The extracted material is then transported to a separate zone for a stage that is significantly more delicate and hazardous. Why is mercury introduced into the processing cycle despite its known toxicity? It seems like a reckless decision, but in reality, mercury is the only affordable chemical available in these regions, capable of dissolving gold and separating it from unwanted impurities. Workers manually knead the ore mixture with the liquid metal for 20 to 30 minutes. One can notice the substance transforming into a gray, dough-like amalgam as the pressure of their hands fuses the gold and mercury together. This toxic mass is subsequently heated over an open flame, causing the mercury to evaporate into the air while leaving behind a residue of raw gold. The procedure remains primitive, functional, and physically devastating for everyone involved in the vicinity. This ancient and lethal methodology stands as the absolute technical opposite of how gold extraction is handled in other parts of the globe. In total contrast to the manual labor found across Africa, the United States has implemented modern machinery and high-precision technology to harvest gold on a massive industrial scale. This sophisticated approach increases the speed of production while simultaneously working to mitigate the long-term environmental consequences. The material is ready to move to the next processing phase without haste. 10 to 20 meters is the average depth of the vertical boreholes drilled into the rugged terrain of a Nevada gold mine. Why is such extreme depth necessary before a single gram of metal is even visible? It would seem that surface excavation could reach the ore deposits directly. But in reality, the gold is locked within massive subterranean formations that require systematic fragmentation. A heavy-duty service truck serves as the mobile foundation for an imposing drilling rig. One can notice how the machine drives steel pipes into the solid rock using immense hydraulic pressure and calibrated force. The drilling process is only gaining momentum. Technicians carefully prepare the next phase by filling these deep cavities with specialized explosive charges. Each individual borehole receives its own detonator, and a single blast site often contains between 50 and 100 of these precise points. Every connection is linked and timed with millisecond accuracy to ensure the energy release follows a specific sequence. The equipment gradually moves to a safe distance before the countdown reaches 0. powerful detonations trigger all at once, shaking the entire landscape with a rhythmic series of concussions. It is visible how dense clouds of gray smoke and dust erupt into the sky as the massive pressure tears through entire sections of the mountain. Boulders split with a loud crack, disintegrating into thousands of manageable fragments that are now ready for the extraction of precious metal. It seems like a scene of chaotic destruction, but in reality, this fragmentation is a calculated necessity for the loading phase. Heavy-duty excavators move into the blast zone as soon as the dust slowly settles. The buckets of these machines scoop up the shattered ore in continuous cycles, lifting several tons with every single movement of the hydraulic arms. They deposit the gold-bearing rock onto a sophisticated system of conveyor belts that stretches along the perimeter of the mining operation. This automated transport network is designed for high-volume efficiency. The belts rotate ceaselessly, moving the material from the site of the explosion toward temporary storage areas without interruption. The ore moves smoothly along the line, transitioning to the next level of processing where the gold will finally be separated from the waste rock. Thus, the raw material reaches the storage phase, completing its first major transformation in the production chain. 100% automation governs the conveyor belts that transport raw ore throughout the processing facility. Why is such massive infrastructure necessary for material that seems to contain almost nothing? At first glance, the rock appears unremarkable, but in reality, every 1,000 kilograms of stone hides exactly 0.05% of precious metal. This means only one single gram of gold is buried within thousands of kilograms of waste material. Yet modern refining technology ensures this microscopic trace is never lost. The process is only gaining momentum. Giant ball mills receive the ore for the first stage of transformation. One can notice the scale of these rotating drums, which are filled with tens of thousands of individual steel spheres. These grinding components range in weight from just a few kilograms to over 27 kilograms each, creating a combined mass of several hundred tons of solid steel. As the massive mill rotates, the heavy spheres are lifted and dropped, colliding with the ore to crush it with tremendous force. Everything only gets more complicated. Rhythmically, the internal steel balls pulverize the boulders into a fine powder over a continuous period of 20 to 30 minutes. The equipment gradually breaks the mineral structure until it reaches the consistency of dust, at which point the release of gold particles becomes significantly more efficient. Water is then introduced to the pulverized ore, creating a thick slurry with the texture of heavy sludge. This specific consistency is vital, as it allows for the seamless separation of gold from the surrounding waste materials. But this is just the beginning. Large open-air tanks receive the flowing slurry to initiate the primary phase of physical separation. It only looks obvious to rely on gravity alone, but in reality, chemical agents like cyanide must be introduced to dissolve any remaining gold that stayed trapped within the mineral particles. This liquid solution, now carrying the dissolved precious metal, is pumped into specialized electrolytic cells where a constant flow of direct current passes through the fluid. The process is only gaining momentum. One can notice how the gold ions respond to the electricity, migrating toward the negative electrode to deposit themselves as a firm, solid layer of pure metal. Every parameter of this electrochemical reaction is maintained under strictly monitored conditions to ensure the resulting gold achieves a purity level of nearly 100%. Once the solid metal is recovered from the electrodes, it is subjected to intense thermal processing in furnaces reaching 1,120 degrees Celsius. The camera glides along the molten stream as the heat eliminates every remaining impurity. At these extreme temperatures, the gold transitions into a liquid state, allowing it to be poured with precision into waiting molds. This melting stage serves a dual purpose, as it also softens the molecular structure to ensure the final bars are uniform and free of internal stresses. The metal takes on its standard commercial form while preserving the high level of purity established during the chemical extraction phase. The material is ready to move to the next processing phase without haste. 1064 degrees is the temperature at which the liquid metal finally begins to stabilize as it cools. Why must the cooling process occur at a slow and natural pace in the open air? It would seem faster to quench the metal in water to save time. However, allowing the gold to settle gradually into the molds prevents internal stresses and surface cracking, ensuring the structural integrity of the final product. The liquid gold takes shape slowly as it is poured into heavy molds. where it is left to solidify under atmospheric conditions. Only looks obvious as a simple cooling stage, but in reality, this controlled thermal reduction defines the metal's physical state. One can notice how the molten surface loses its liquid shimmer and transforms into a hard, brilliant solid with a clean, rectangular geometry. This is just the beginning. The equipment gradually shifts the solid blocks onto a high-precision electronic scale to determine the exact weight of each unit. On average, each gold bar weighs between 1 and 2 kilograms. It is visible how the metal reflects the ambient light, showing a clean appearance that defines a standard commercial bullion. But this is not the limit. Each individual bar contains approximately 99.99% pure gold, with less than 0.01% residual metallic impurities remaining after the primary smelting. Everything only gets more complicated. After the weighing and inspection phases are complete, the metal undergoes a chemical cleaning process using a mild acid solution. At first glance, the bars appear clean, but in reality, microscopic impurities such as heavy metals and chemical compounds from the melting process still cling to the surface. The camera glides along the washing station as the mild acid dissolves these contaminants without affecting the pure gold underneath. The process is only gaining momentum. The pure gold bars are then transported to the primary banks of the United States, including the Federal Reserve, for long-term storage. There, they are placed within high-security vaults under the constant surveillance of professional security personnel. The equipment and facilities are designed to ensure maximum safety and absolute confidentiality for every kilogram. Having traveled the path from initial explosion to final fusion, the pure gold bar is now finished. But its technical history does not end at this stage. It seems simple to view gold as a static asset, but in reality, its physical properties are extraordinary. One can notice that the metal is so malleable that it can be drawn into wires finer than silk threads. During the 19th century gold rush, entire cities and farms were abandoned as thousands of people pursued the hope of sudden wealth. Most of the easily accessible gold on the planet has already been extracted, forcing modern miners to penetrate deeper into the earth than ever before. Transition to the next level. Initially, 19,000 tons of rock were required to yield just 260 grams of gold. Now, those same 260 grams, after passing through fire and chemical refinement, reach the hands of specialized jewelers. One can notice the transition as the metal moves from industrial bars into artistic manufacturing. It gets more complex further on. The refined gold is transported to specialized facilities where it is reheated in high-temperature furnaces to increase its softness and malleability. Once it reaches the desired level of flexibility, the gold is fed through powerful rolling mills. Intense pressure from the rollers flattens and stretches the metal into long, thin strips or delicate wires. The equipment gradually narrows the diameter of the gold until it meets precise specifications. The thin gold wires are subsequently sent to a specialized chain-making machine where they are wound and shaped. The metal lays in an even layer as it is manipulated into small, precise links. Each individual link is carefully formed to ensure the consistency of the final jewelry piece. The process concludes this phase, opening the road to formation. 110 million tons of paper and cardboard are discarded every single year within the borders of the United States alone. Why is such a staggering volume of waste considered a strategic resource rather than a burden? At first glance, this mountain of refuse seems like an environmental catastrophe, but in reality, it serves as a primary source of industrial raw material. With this quantity of fiber, it would be possible to construct a continuous wall of boxes stretching all the way to the moon and back to Earth. The process is only gaining momentum. Hidden within the life cycle of every discarded container lies a technical secret regarding its structural longevity. A single fiber of this material can undergo the process of rebirth not once or twice, but up to 7 times before losing its integrity. One can notice how something destined for a landfill transforms into the mechanical backbone of global commerce. Every glittering gram of processed material carries a history of technological power and the precise cost of human labor. These are the two inseparable sides of the same precious industrial metal. Everything only gets more complicated. That cardboard box arriving at a doorstep is often opened and discarded without a single thought. It does not mark the end of a narrative, but rather the commencement of an epic industrial journey through specialized facilities. The transition begins amidst the logistical chaos of daily consumption in supermarkets and massive e-commerce fulfillment centers. In these locations, the volume of discarded material is truly colossal, requiring immediate mechanical intervention to manage the flow. The equipment gradually organizes the mass. Powerful hydraulic presses activate with a steady hum to compress mountains of loose boxes into dense, uniform bales. Each of these cubic units reaches a weight of nearly 1,000 kilograms as the metal rams force the air out of the fibers. These compressed cubes represent the initial step in converting environmental chaos into industrial order. Thousands of these heavy bales are loaded onto transport trucks every day to begin a long pilgrimage toward regional recycling centers. It gets more complex further on. As the vehicles reach the factory gates, the air vibrates with the mechanical roar of colossal intake machinery. Every truck is weighed on precision scales, and every bale is catalogued before being descarrigated for the opening phase of the operation. Here, the first battle in the technical war against contamination commences on the conveyor belts. One can notice how human inspectors and advanced optical sensors work in a synchronized, implacable line of defense. The sensors scan for specific molecular signatures. Their mission is to identify and extract the primary enemies of the recycling process before they reach the pulpers. This includes fragments of plastic adhesive tape, forgotten metal staples, nylon filaments, and any trace of organic grease or excessive moisture. A single oversight at this stage can compromise several tons of high-grade raw material during the melting phase. A contaminated bale results in the ruin of an entire production lot, leading to significant energy and resource losses. The process is only gaining momentum. Following this rigorous manual and automated sorting, the bales are categorized by their specific physical properties and fiber lengths. The robust corrugated cardboard is separated from the elegant flatboards and containers featuring high-density color printing. Each category is assigned to a distinct processing stream, as the quality of the final product depends entirely on the purity of the initial sort. The material moves toward the heavy machinery, where the next phase of structural transformation waits to begin. Molten streams of fiber go further along the production chain. 1,000 kilograms is the exact weight of each individual bale of cardboard arriving at the primary processing zone. Why must these compressed blocks be reduced to a chaotic liquid state after being so carefully organized? It would seem that maintaining their solid form would be more efficient for transport, but the industrial reality is that only by returning the material to its fibrous essence can it be reborn as a new product. This transformation relies entirely on the immense physical power of water. One can notice the massive scale of the hydropulper, a giant steel cauldron engineered to hold tens of thousands of liters of liquid. The process is only gaining momentum as the bales are dropped one by one into this artificial vortex. It only looks obvious that the water acts as a simple solvent, but in reality, it is a controlled force of nature. Massive rotor blades serve as the mechanical heart of the machine, spinning at several hundred rotations per minute. This motion creates a turbulence so violent that the multi-layered structure of the cardboard is fundamentally disintegrated. One can notice how the hardened glue holding the sheets together is ripped away by the sheer force of the currents. Hard coatings of plastic and remnants of industrial inks are stripped from the cellulose like old skin. But this is just the beginning. The equipment gradually dilutes the mixture until it reaches a state where only 1 to 2% is solid fiber, and the remaining 98 to 99% is pure water. At first glance, this extreme dilution seems wasteful, but it provides every individual fiber with the necessary space to be attacked by the water from all sides. This deep cleaning ensures that each strand is separated from its neighbors. The result is a thick brown slurry, a uniform mass of cellulose that represents the first glimpse of a new life for the material. Everything only gets more complicated as the paste remains coarse, impure, and structurally weak at this stage. These fibers resemble tired muscles that require reconditioning and strengthening at a level invisible to the naked eye. To give the chaotic soup the necessary strength, a new structure must be built through mechanical refinement. The paste is pumped into specialized refining machines, where it's forced between rotating discs equipped with microscopic blades. It is visible how the equipment delicately deflects the fibers rather than cutting them. This specific action fibrillates the surface of each cellulose strand, forcing it to open up countless tiny arms. Transition to the next level. These microscopic extensions will later intertwine to create a molecular bond of incredible strength. However, every cycle of recycling inevitably incurtains and weakens the structural integrity of the fibers. To rejuvenate the mixture, the factory injects fresh material in the form of virgin pulp extracted directly from natural wood. This injection of new blood provides the necessary reinforcement for the veteran fibers. The blend of old and new material continues its journey through the automated system toward the final formation. 100% of the structural integrity of a high-quality cardboard box depends on the precise ratio of recycled materials to virgin cellulose. Why blend these two seemingly opposite materials together? It only looks obvious to use one or the other, but in reality, the recycled components provide environmental sustainability, while the fresh recruits of virgin fibers ensure maximum mechanical resistance. But this is just the beginning. The outer layers of the future containers require a surface that is both smoother and more rigid, which is why they receive a significantly higher dose of long virgin fibers during the mixing phase. In contrast, the internal structure, the fluted medium, is composed almost entirely of recycled matter to optimize resources. However, the technical formula remains incomplete without the integration of chemical additives. One can notice how starch is introduced into the suspension to provide structural rigidity to the fibers. At the same time, specialized sizing agents are added to precisely regulate water absorption, while chemical resins increase the material's overall resistance to ambient humidity. The equipment gradually transforms what was once a coarse paste into a high-technology raw material. This suspension is perfectly calibrated, purified of all contaminants, and prepared for the next stage of industrial creation. The prepared pulp, which now consists of 99% water, begins its rapid journey toward the paper machine. This piece of industrial hardware is an engineering marvel stretching for hundreds of meters through the facility. A thick brown torrent of liquid is poured with absolute uniformity onto a vast wire screen that moves at a dizzying velocity. Transition to the next level. Gravity and powerful vacuum systems begin to pull the water downward through thousands of microscopic openings in the mesh. The water separates from the solid components, leaving behind a thin, concentrated layer of cellulose on the surface of the wire. One can notice how the fibers, now liberated from the liquid that kept them apart, begin to settle and interlace into a delicate web. Giant press rollers situated beneath the screen gently squeeze out additional moisture while compacting the new formation. It seems simple to remove water, but in reality, this is where the liquid transforms into a solid state. Where a shapeless flow existed seconds before, a continuous sheet of pale, damp paper now emerges. Laser sensors monitor every single millimeter of the surface, measuring thickness, uniformity, and moisture levels to ensure no defect interrupts this delicate birth. The process is only gaining momentum. A new sheet of paper has been formed, yet it remains completely saturated with liquid. Containing more than half of its total weight in water, the material is currently fragile and highly vulnerable to tearing. To acquire its legendary durability, the sheet must now face a rigorous challenge of thermal energy and mechanical pressure. The damp, trembling sheet is guided into the heavy press section. There is no delicacy in this part of the machine, as pairs of massive steel rollers, each weighing more than a standard automobile, squeeze the sheet with a force equivalent to hundreds of tons. The water is literally crushed out of the fiber structure, forcing the cellulose strands to unite in a more intimate and powerful bond. The sheet thickness is stabilized and its surface is smoothed, but the brute force of mechanical pressure alone is not enough to complete the transformation. The material is now stronger, yet it still requires further processing to reach its final industrial specifications. The molten stream of production goes further along the chain as the sheet enters the drying phase. 100 meters is the minimum length of the thermal tunnel where the damp material enters the critical drying section. Why is such an immense distance necessary for a process that seems like simple heating? A shorter path would force an abrupt temperature spike, but the moisture must be extracted with surgical precision to prevent the structural collapse of the fibers. The sheet serpents through this incandescent labyrinth, moving across dozens of massive hollow cylinders made of polished steel. High-pressure vapor fills the interior of these rotating drums, raising the surface temperature to over 300 degrees Celsius. One can notice how the equipment radiates a level of heat that surpasses even a standard industrial pit furnace. The paper glides over each hot cylinder at a constant speed, allowing the heat to evaporate the remaining moisture in a gradual and strictly controlled manner. This phase is governed by a delicate physical balance. If the evaporation occurs too rapidly, the paper becomes brittle and loses its flexibility. Yet if the speed is too slow, the entire production line grinds to a halt. It only looks obvious to heat the material, but in reality, a constant flow of hot air must circulate around the rollers to maintain an exact equilibrium between ambient humidity and surface temperature. The process is only gaining momentum. Upon emerging from the far end of the tunnel, the moisture content of the sheet has plummeted from over 50% to a mere 5%. The transformation is visible as the material becomes dry, strong, and dimensionally stable. The finished sheet, appearing as a continuous web several meters in width, is finally wound onto giant spindles to form massive coils. 3 meters is the diameter reached by these finished reels, which weigh several tons each. But this is not the limit. While the paper now exists, it still lacks the structural rigidity required for a heavy-duty box. The secret to its final strength lies in the next phase of the operation. These massive rolls of flat paper serve as the primary raw material for the final and most technically ingenious stage, known as fluting. The equipment gradually feeds a single sheet between 2 steel rollers, equipped with deep grooves that mesh together like massive mechanical gears. High temperature and intense pressure work in tandem here, forcing the flat paper to adopt a continuous and mathematically perfect wave shape. At first glance, this geometric change seems simple, but in reality, it is a masterpiece of engineering. This corrugated structure, or fluting, exponentially increases the ability of the material to resist vertical compression without adding any significant weight to the final product. One can notice how each individual wave acts as a miniature engineering arch, distributing downward force with incredible efficiency. The fluted core, however, is merely the skeleton of the final board. Transition to the next level. To become a complete and functional structure, the corrugated center must be encased. An automated system applies fine and highly precise lines of high-performance adhesive to the apex of every single wave. Immediately following the application, 2 flat sheets of paper known as liners are pressed firmly against the top and bottom of the fluting. This creates a high-strength sandwich of materials. This new 3-layered sheet moves forward, transitioning into a calm stage as the adhesive begins to set. 100% of the material, now known as corrugated cardboard, moves through a series of heavy industrial rollers that ensure a perfect mechanical bond between the layers. Why is this specific structural alignment so critical for the final product? The compression looks like a simple passage of paper, but without this pressure, the layers would separate under the slightest tension. The result is a material that is simultaneously lightweight, inexpensive, and surprisingly robust, serving as the fundamental base for nearly every packaging unit in the world. It gets more complex further on. One can notice how high-speed industrial blades slice, crease, and fold these sheets into the infinite varieties of boxes found in global logistics. Each finished unit functions as a small paper fortress, protecting its contents through geometric rigidity. But can this cycle of fiber recovery continue forever? Only at first glance does the process seem infinite, but in reality, physics imposes strict limits on the material. Cellulose fibers become progressively shorter and significantly weaker after being recycled between 5 and 7 times, eventually losing the ability to form a resilient cardboard structure. The process is only gaining momentum. Even at this point of exhaustion, the value of the material does not disappear entirely. These fatigued fibers are redirected for the manufacturing of less demanding products, such as molded egg cartons or paper napkins. One can notice a similar efficiency in the glass production industry, where adding just 10% of recycled material reduces total energy consumption by 3%. This proves that recycling functions as a powerful force across the entire industrial landscape. Therefore, the cycle closes with mathematical precision. What began as a single crumpled box in the corner of a warehouse is reborn as thousands of new packaging units, perfectly formed and ready to protect the goods that drive the global economy. Each container seen on transport trucks, in distribution centers, or at a doorstep acts as a silent witness to this massive industrial transformation. Every single ton of recycled paper represents 17 trees that remain standing in the forest. It also accounts for 26,500 liters of water saved and 1 full ton of carbon dioxide that never reaches the atmosphere. Transition to the next level. The equipment gradually processes these remnants, ensuring that the next time a cardboard box is held, its incredible journey is recognized. This is not the act of discarding waste, but rather the first step in the next life of the material. A different kind of substance, marble, is visible everywhere from ancient palaces and museums to modern luxury kitchens. It remains a universal symbol of wealth, high art, and eternal durability. It only looks obvious that such a smooth surface is easily obtained. Why does the production of a perfectly flat slab, polished until it shines like a mirror, require such violent beginnings? The answer is not an elegant one, and it does not start with the hand of an artist. It begins with a calculated battle against the earth itself. To extract a single block of this stone, engineers must first declare war on the geography of a mountain. They must remove 70 feet of entirely useless topsoil and overburden. 21 meters is the exact depth of this unwanted layer, which is equivalent to the height of a 7-story building. 7 stories of clay, common stone, and debris must be pulverized with precisely placed explosive charges. This massive clearance is performed solely to reach the high-quality stone that lies beneath the surface. One can notice the dust settling in slow clouds after the detonation reveals the white vein of the deposit. But this is just the beginning. The real challenge and the true miracle of modern engineering lie in the handling of the raw material. It involves taking a colossus weighing 40 tons, torn directly from the mountain, and beginning its transformation into a finished product. The equipment moves with a slow tilt of the boom as the journey of the stone starts. Thus, the material leaves the quarry, transitioning into a calm stage of precision cutting. 70 feet is the total thickness of the outer layer of the mountain that engineers must penetrate before reaching the valuable material. This dense shell, consisting of clay, silt, and loose rubble, acts as a protective fortress for the marble hidden beneath. Why is such massive effort spent on a layer with zero commercial value? Extraction is impossible without its complete removal. The presence of this overburden prevents any direct access to the veins, requiring its systematic destruction to expose the prize below. One can notice how drilling teams establish a precise grid of deep boreholes across the mountain surface. These vertical shafts are filled with carefully measured explosive charges to ensure the force is directed exactly where needed. This process is not a chaotic demolition, but rather a form of surgery performed with dynamite. It seems simple to just blow up the mountainside, but in reality, every gram of explosive is calculated to avoid damaging the structural integrity of the quarry. The warning siren sounds across the excavation site with a sharp, rhythmic tone. A heavy moment of silence follows as the countdown reaches its conclusion. Then, the mountain explodes with a muffled roar that vibrates through the bedrock. One can notice a massive cloud of white dust rising slowly until it obscures the sky. Thousands of tons of earth and worthless stone are torn from the face, cascading down the quarry walls in a controlled landslide. Dust slowly settles in thick layers, finally revealing the exposed marble vein. At this exact moment, the operational strategy undergoes a radical transformation. While explosives were necessary to clear the path, they cannot be used on the marble itself, as an excessive impact would shatter the internal structure of the stone and render the prize useless. Now, the reliance on brute force gives way to absolute precision. The process is only gaining momentum. The equipment gradually transitions to using a specialized cutting tool known as a diamond wire. It only looks obvious that a cable could cut stone, but this is a high-strength steel rope several feet in thickness encrusted with industrial diamonds, the hardest material on the planet. Engineers pass this wire through precisely drilled intersecting holes to create a continuous loop around the block. The machinery activates with a high-pitched, constant hum that resonates against the stone walls. One can notice the diamond wire begins to saw through the solid rock at a steady, relentless pace. It gets more complex further on as the friction generates intense thermal energy. Simultaneously, high-pressure pumps force a continuous stream of water directly into the deepening cut. The water serves to cool the diamond segments and flush out the fine stone slurry to prevent the cable from seizing. The liquid flows darkly from the crevice, carrying away the debris of the cut. The process continues its slow progress into the heart of the mountain. Two distinct missions are performed simultaneously by the continuous stream of water during the cutting process. Why is a constant liquid supply necessary for the diamond wire? It seems simple to just let the steel cable run, but the water serves to cool the wire to prevent it from melting under intense friction while washing away the marble paste, which is the fine white powder that forms as the stone is ground. The diamond wire moves with a speed that appears agonizantemente slow as it penetrates the rock face centimetro by centimetro. As the groove becomes progressively deeper into the mountain, workers insert specialized hydraulic jacks into the narrow opening. One can notice how these machines apply a silent force of hundreds of toneladas, beginning to push against the massive structural resistance of the stone. A deep groan echoes through the quarry, signifying the sound of the stone finally surrendering to the mechanical pressure. 40 toneladas is the weight of the massive block that finally separates from the mountain face, standing as tall as a 3-story building. But this is just the beginning. The freed 40-ton block immediately transforms from a geological feature into a 40-ton logistical problem. This mass is equivalent to the weight of 30 medium-sized cars or 6 full-grown adult elephants combined. It is impossible to simply drag the stone across the ground, as the risk of fracturing the material is far too high for such a valuable resource. The process is only gaining momentum. The stone must first be moved with extreme caution to a waiting yard, which serves as a flat and secure staging zone located within the quarry perimeter. This is the moment where the true giants of the industry enter the scene. Heavy crawler cranes, machines engineered specifically to lift impossible weights, move into their precise positions around the block. Massive steel chains are secured to the stone. One can notice that the links of these chains are the size of a human head to ensure they do not snap under the immense load. The crane motor begins to labor with a deep, vibrating roar as the tension in the steel chains reaches its absolute limit. The operator must be a master of the machine, utilizing millimetric precision to ensure the stone colossus is hoisted from the ground without swinging. It gets more complex further on. The block is then lowered with careful deliberation onto a vehicle that hardly resembles a standard truck. This is a low-profile platform trailer equipped with multiple heavy-duty axles. Why are so many axles and dozens of wheels required for this single transport? To the eye, the trailer looks overly complex, but 40 toneladas concentrated on only a few wheels would instantly destroy the structural integrity of any road surface. By distributing the pressure across dozens of independent wheels, the massive weight becomes controllable and safe for transit. Safety checks are performed 2 or even 3 times as the block is secured with additional heavy-duty straps. The journey begins at a pace that is the slowest one can imagine. The truck moves at a snail-like speed, struggling as it climbs the steep and winding mountain roads. One can notice the equipment gradually navigating the terrain, where every curve represents a complex logistical challenge for the driver. Each descent tests the braking systems to their absolute mechanical limits. This slow-moving convoy is tasked with transporting the raw material from its original geological home to the factory. Everything only gets more complicated at the next facility, where the true transformation of the stone will finally begin. The material leaves the mountain, transitioning into a calm stage of transport toward the processing plant. 40 tons is the exact weight of the massive block as it arrives at the processing facility. Why does the atmosphere inside these walls shift so dramatically compared to the quarry? At first glance, one might expect the scent of explosives and dust to linger, but in reality, the air here is heavy with the smell of wet stone and cold metal. This shift in environment marks the transition from raw extraction to precision engineering. The block is positioned onto a heavy cutting platform, where it must be secured with absolute immutability. Giant hydraulic clamps descend with a low hiss, fixing the stone in place with immense force. If the material shifts by even a single millimeter during the subsequent hours of work, every slab produced will be uneven, rendering the entire process a failure. A machine known as the gang saw or frame saw waits to receive the load. This structure is a monumental piece of engineering designed to support and process weights that would crush standard machinery. Its primary component is a massive rectangular frame that holds dozens of parallel steel blades in a rigid formation. But this is just the beginning. The machine begins its operation with a rhythmic and deafening roar that fills the entire hall. Like the teeth of a giant comb, the frame moves back and forth, creating a hypnotic and brutal cadence. One can notice how the blades, coated in industrial-grade abrasives, descend at a rate of only a few millimeters at a time onto the block, which measures 2 meters in thickness. It gets more complex further on. Simultaneously, a continuous torrent of water mixed with abrasive sand pours directly into the incision. This slurry serves as a lubricant and a cutting agent, helping the metal blades bite into the dense crystalline structure of the stone. The noise is constant and overwhelming as the friction generates intense heat. 12 to 20 hours is the time required for the machine to complete the passage through a single block of marble. It is visible how the process continues without interruption, stretching across an entire working day or longer just to divide a single stone. In this factory, patience is a technical requirement rather than a virtue. Eventually, after nearly a full day of mechanical labor, the blades emerge from the bottom of the material. The one solid cube has been transformed into a giant deck of cards, consisting of a series of stone slabs, each weighing several hundred kilograms. Transition to the next level. At this stage, the slabs appear lifeless and dull. They are rough to the touch, their colors are pale and muted, and they remain coated in the gray mud left behind by the cutting slurry. The camera glides along the surfaces, showing that the famous beauty of the marble remains entirely hidden beneath this industrial residue. Now the transformation begins in earnest. Automated robotic arms enter the workspace with calculated movements, as no human hands are used here due to the weight and fragility of the stone. Giant vacuum suction cups descend with a sharp hiss of air, gripping the slab before lifting it into the workspace. It gets more complex further on. The robot places the slab onto the polishing line, which functions as a long tunnel of physical transformation. The stone slides beneath the first station, where a set of rotating heads begins to spin. These heads are equipped with coarse abrasive discs designed for the initial phase of resurfacing. The sound is a harsh, violent scraping of stone against industrial grit. As the slab moves forward, the second station utilizes discs with finer grains, and the pitch of the grinding shifts higher. By the time it reaches the third station, the grains are even smaller, and the surface begins to lose its jagged texture. The slab must pass through a minimum of 7 or 8 distinct stages of sanding. Each successive step is designed to remove the microscopic scratches left by the previous disc, making the surface progressively smoother. Throughout this entire duration, tons of water are pumped over the stone to cool the high-speed discs and wash away the accumulating marble paste. Everything only gets more complicated as the material reaches the final station. This stage does not utilize abrasive grains, but instead employs a specialized chemical polishing compound. One can notice the head spinning at maximum velocity, and suddenly, the visual properties of the stone change. Where there was once only dull gray rock, a perfect mirror finish begins to emerge. Thus, the material reaches the standard ready for the further stage. 400 kilograms of stone glide beneath the polishing heads, transforming a dull gray slab into a deep, light-reflecting surface where colors suddenly explode with newfound intensity. Why is this mechanical polishing not the final stage of the process? At first glance, the slab appears flawless as the hidden veins, concealed for millions of years, are finally revealed in their full complexity. But in the global luxury market, visual perfection is merely a superficial requirement that does not guarantee structural integrity. The most dangerous defects, which can result in losses totaling millions of dollars, are those that remain completely invisible to the naked eye. The polished slab moves slowly on a conveyor system toward a specialized dark chamber. One can notice how intense beams of red light sweep across the stone in a systematic pattern as part of the laser inspection system. The equipment gradually performs tasks that the human eye is incapable of achieving by measuring flatness with micron-level precision and searching for internal micro-fissures. A single tiny air bubble trapped within the mineral structure or an invisible tension line resulting from the original quarry explosion can be identified instantly. The computer analyzes the high-resolution image data in real time to ensure total compliance. Everything only gets more complicated as the sensors detect even the smallest internal imperfection. If a flaw is found, the system marks the slab with a red indicator, and it is immediately rejected. The process is only gaining momentum. Even after hours of intensive processing and polishing, the stone is discarded if it fails this digital scrutiny. Slabs that successfully pass the laser scanning phase are then transferred to a station for human inspection. Experienced workers slowly pass their hands over the cold surface, feeling for tactile flaws or subtle texture changes that the automated machinery might have overlooked. While the digital systems are highly advanced, they cannot yet replace the intuition gained from decades of physical experience with natural stone. The slabs that receive final approval are washed with high-pressure water jets to remove every particle of residual dust. But this is just the beginning. Packaging requires extreme caution because each individual slab can weigh more than 400 or even 500 kilograms. Robotic cranes equipped with suction grippers lift the heavy stone and stack them onto reinforced steel pallets. It is visible how the workers ensure the slabs never touch one another, as direct stone-to-stone contact would be fatal to the polished finish. Therefore, employees manually insert protective sheets of foam or specialized rubber between every single layer. The entire assembly is secured with high-tension steel straps before being shipped to the most prestigious architectural projects on the planet. Not every piece of extracted marble is destined to become a floor for a luxury hotel. The process is only gaining momentum for the highest quality materials. The most pristine blocks, characterized by their purity and a minimal density of veins, are diverted toward a different destination. They are sent directly to the studio of a master sculptor. Transition to the next level. At this stage, the industrial rules of mass production are completely abandoned. There are no automated robots, no laser scanning arrays, and no moving assembly lines in the sculptor's environment. The artist begins the creative process with detailed manual drawings or advanced three-dimensional scanners to meticulously plan every single structural cut. Initial material removal is a loud and aggressive process. Large diamond-tipped saws and heavy pneumatic hammers tear away significant chunks of the stone to establish the basic silhouette of the work. But then, the mechanical noise stops completely. It seems simple to remove the excess, but the true work is only starting. The sculptor picks up small manual hammers and sharp steel chisels. In this environment, the stakes are absolute and unforgiving. In a factory setting, a broken slab is merely a calculated production cost or a minor material loss. In the studio, a single misplaced blow or 1 millimeter of excessive force can instantly ruin the entire piece. Months or even years of dedicated labor can be destroyed in one single second of distraction. One can notice the total focus of the artist, as there is no undo button and no way to repair the stone once it is removed. The artist works with extreme patience, utilizing pointed chisels to define lines and flat chisels to smooth out larger surfaces. When the final shape is eventually achieved, the sanding process begins. The material is worked by hand with the same consistent form until the desired finish is reached. Thus, the stone completes its transformation, ready to exist as a finished work of art.